Okay, I think the recording's going. My name is Lucas. Today we're going to be talking about cardiogenic shock versus all the other different types of shock. And so this is the type of question that you're going to be faced with in order to answer on step one and step two. This question is going to ask you the difference between all the different types of shock and be able to pick one out of, basing out of a clinical vignette. And in order to do that, we really have to have a good understanding of what shock is and what are the different types of shock and how to understand the different types of shock and how they differ from one another. So how can we do that? Let's talk about shock first. Shock is how it's defined is the global fall in tissue perfusion as to inadequately meet the metabolic demands of the body. So what that means is, all of our tissues and organs, they all need perfusion. They all need blood to reach, and not only blood to reach, but blood to push on the walls of the capillaries to be able to push nutrients and oxygen into the cells. Anytime that is impeded, you're at risk of shock. What is shock not? Well, it's not ischemia. Ischemia is the regional loss of tissue perfusion. We're talking about a global thing here. An example of ischemia that wouldn't be shock would be like a transient ischemic attack that would happen in the brain. Okay, so how can we understand shock on a better mathematical level? This is the equation that we like to share with students to be able to help them understand better. And you notice how it mimics Ohm's law that we learned for the MCAT. So what we have is mean arterial pressure. The mean pressure in your arterial system is equal to the cardiac output, or how much volume is being pumped by the heart per minute, times the systemic vascular resistance, all the resistance of your arterial system. CO can be further broken down into heart rate times stroke volume, and stroke volume can be further broken down into end diastolic volume, how much blood is going to be in the heart at the end of diastole, in the left ventricle at the end of diastole, and how much blood is left after the end of systole. So you subtract those things, that'll tell you how much blood left the heart after a good squeeze, after the end of the systolic phase. So why do we talk about this equation? Well, it helps us be able to track the changes to eventually understand why there's a fall in mean arterial pressure. Now, why do we care about a fall in mean arterial pressure? Well, like I said, with shock, what causes that is basically a fall in pressure, at the risk of oversimplification, a fall in pressure where you're not able to perfuse the tissues anymore. So let me give you an example of how something could translate into a fall of mean arterial pressure. In the case of cardiogenic shock with an MI, part of the heart muscle is dying, and then you're not able to pump as hard. If you're not able to pump as hard, there's going to be more left over in the heart after systole, so you're going to have a lot larger end systolic volume. That larger end systolic volume will make this term smaller, make this term smaller, make this term smaller, and then of course, if this equal sign is to remain the same, remain true, then you're going to have a fall in mean arterial pressure. You would do the same for all the different types of shock. So hypovolemic shock, obviously you have less circulating volume due to potentially hemorrhage or vomiting or diarrhea. That means less cardiac output, less volume to circulate in the body. So that would cause a decrease in mean arterial pressure. Obstructive shock would cause actually a decrease in preload, how much blood can make it back to the heart. So, what could cause that? Tension pneumo, PE, cardiac tamponade, all of these things could potentially cause a decrease of preload. So blocking at some point before the lungs, blood being able to reach the lungs and then eventually being able to go to the left atrium, the left ventricle, and be pumped to the rest of the body. For distributive shock, what ties those subcategories together is going to be a fall in systemic vascular resistance. We understand that for sepsis, for anaphylaxis, these are just in over proportional or out of proportion responses, immunologic responses to some sort of antigen or to bacteremia or sepsis. So that's what's going to cause the fall in systemic vascular resistance. Neurogenic shock is also going to have a fall in systemic vascular resistance and a fall in heart rate because you have some sort of trauma or some sort of condition where you're cutting off the neural input to the rest of the body that would allow you to mediate a sympathetic response. And in any case, all of them are going to decrease systemic vascular resistance. And in fact, that of course is going to decrease your mean arterial pressure. So now knowing what we know, I would encourage you on your own time to understand why all these arrows are going up and down. Part of that, why an arrow would go up or down would be because it's the cause. For cardiogenic shock, we know the cause of cardiogenic shock is going to be a fall in cardiac output, and the rest of it is going to be response. So go ahead on your own time and make sure you understand why these arrows are going up and down. Now we can go back to the question. and be able to answer it. This is a case of severe chest pain, so we're immediately being able to cross off some of the other types of shock that wouldn't be associated with chest pain. Obstructive shock and cardiogenic shock are what we're left with. This could be an MI, this could be a PE, this could be a tension pneumo, something like that. But then we're also told that there's an S3 gallop and there's ST segment elevations. So this is going to point us toward a cardiogenic cause of that shock. So that's going to lead us to choose A. But yeah, this is a crash course in shock and all the different types of shock. And if you have any questions, I'd love to answer them at this point.